Okay, good morning, everyone. Let's begin our lesson. So last week, we talked about the CVD and the PVD. We mentioned for this slide, we mentioned the advantage of the CVD includes the good film quality, and also it has the conformal step coverage, and also the high growth rate. This growth rate means high deposition rate. Okay. And also it can deposit the materials which are hard to evaporate. Usually, we need to use the PVD to do the evaporation. 我们用 PVD 来做这些热的蒸镀、电子束的蒸镀，都一般是用 PVD. But for some material, like the tungsten has a very high melting point, so it's very difficult to use the E-gun evaporator to deposit the tungsten. So that's the reason we need to use the CVD. CVD can deposit the material which has the higher melting point. So that's the reason in industry we always say CVD tungsten, CVD tungsten. It means the tungsten, we deposit the tungsten by using the CVD, okay? However, you need to know for the CVD, just for example, you see, we talk about the gate oxide material is the hafnium oxide, and those two are the precursor. Precursor is the reactant, or the reactant for the hafnium oxide. You see, those material are organometallic compound, 金属有机化合物. So you see how you have some organic and it includes the carbon. So that's the reason how we mentioned for the CVD, the disadvantage will be it has the high impurity, like the carbon. So that's the reason in industry we will detect the carbon all the time, because we need to make sure due to this precursor, is the carbon will remain in the hafnium oxide or not. So we will detect the amount of the carbon inside the film. We need to know the film quality. So that's the reason we need to monitor the amount of the carbon, okay? And also, for the CVD, when you see the precursor, it's very, it's not a very simple, it's not a very simple compound. So usually all of these precursor is toxic or corrosive gases, or it's not so, I cannot say it's not safe, but I mean you need to have some facility to deal with all of these kind of gases inside the industry, okay? And also the process temperature is higher. For the PVD, we can deposit the film under room temperature. You see, for the PVD, we can deposit the film under the room temperature for the PVD. However, for the CVD, we need to use the high temperature, or we need to use the plasma to dissolve all of these compounds into hafnium element, for example. So it's required temperature or plasma to provide the energy to break down this covalent bond, okay? Therefore, we can have the hafnium element to become the hafnium oxide, okay? So it's required energy. That's the reason for the CVD. For the CVD process, it requires some temperature, or plasma to provide the energy, okay? Okay, so you need to know some important information from this slide. You need to tell the difference between the PVD and CVD, okay? Okay, so for the following chapters, we are going to talk about different kinds of the CVD for these pages. I believe you can read by yourself. There are several sequences of processing steps for the CVD. or it's the chamber, or it's the chamber of the CVD, and silicon substrate is here, and precursor is from the gas delivered here. So precursor is also the gas phase. Or after the reaction, in here, after reaction on the silicon wafer, or finally we have some byproduct, and byproduct is also 副产物. Byproduct is also the gas phase. Byproduct is also the gas phase. So we can use the vacuum system to pump away the byproduct, because byproduct is also the gas phase. Okay, and the reactant is the precursor. 反应物 reactant, we call it precursor 前驱物. You can say it's the reactor 反应物, and maybe you also can say precursor 前驱物 precursor. Also, we use precursor a lot in industry. Okay, precursor is also the gas phase. And then, finally, the thing you want to deposit will be the solid phase. Okay, so only the thing what we want to deposit on the silicon wafer is the solid phase. Okay, and other byproduct will be the gas phase, and also the reactant or precursor is also the gas phase. Okay. So you can see all of the sequence, okay, by yourself. Okay, you can read by yourself. Okay, and we do have 1 to 8. So you can read by yourself. Okay. And this slide just for your reference. Okay. So today we use the silane SiH4. To become the precursor, become the reactant. And finally, we want to deposit the silicon. So silicon is the solid phase. And you see the precursor is the gas phase. And the H2 is the byproduct we want to pump away. So H2 is also the gas phase, okay? And all of this process is very complex. And it's not the total process. Or sometimes we still have many equations, but we don't consider about it. Okay, so you don't need to memorize it. You just need to know it's a very long and complicated process. Also, sometimes we cannot write all of the equation here to show you how can we deposit the silicon. So during this process, we still have many processing steps during this slide, just for your reference, okay? Okay, so for the following 3 pages, I want to show you the growth rate or deposition rate limiting step. What does that mean? It means today the slowest step can decide the speed of the process. The speed of the process means the growth rate or the deposition rate, or maybe we can just write down as the growth rate, okay? And there are 2 mechanisms when we talk about the oxidation. We mentioned the first one is the reaction rate limited. Reaction rate limited. What does that mean? It means today if I want to decide the growth rate, there are 2 factors. The first one, we need to know if we have the sufficient reactant. If we have the sufficient reactant. If we have the sufficient reactant or not. And the other one is, do we have the sufficient energy? Energy, for example, like the temperature. Okay? Today, if we want to know the growth rate or the deposition rate of the same thing, there are 2 factors to determine the growth rate. The first one is do we have the sufficient reactant or not? 我们有没有足够多的反应物 ？Do we have enough reactant or not? And the second factor will be, do we have the sufficient energy? Sufficient energy means, do we have enough temperature? Do our temperature is high enough or not? Okay. So today, the slowest step will design the growth rate. It means today, if we don't have enough reactant, then this reactant will determine the growth rate. And today, if we have a lot of reactant, if our reactant, we have so many reactant, then the temperature will determine the growth rate. Okay. And today, if we don't have a lot of reactant, then the amount of the reactant will determine the growth rate. Okay. So like the first one, today, if we have a lot of, today the first case here means, if we have enough reactant, if we have so many reactants, then we don't have enough energy. So the first mechanism shows you, we call it reaction rate limiting. It means today, if we don't have the sufficient energy, then the temperature will determine the growth rate. Okay. If we don't have the sufficient energy, then the temperature will determine the growth rate. Okay, the temperature will determine the growth rate, because today we have a lot of reactant, but I don't have enough energy. So today, the temperature will dominate the growth rate. So today, the temperature is very, very important. So that's the reason we can call it reaction rate limiting. So we also can say it's the kinetically controlled, because we don't have enough temperature. So for example, if the deposition temperature, today, if the deposition temperature is 250 versus the 300 degrees Celsius for the deposition temperature, and if you can increase the deposition temperature, the growth rate will be enhanced. Because right now we already have a lot of reactant, we don't need to consider about the reactant, but we don't have the sufficient energy. So the temperature will determine the growth rate. So you just can increase the temperature, then growth rate can be enhanced. Okay. Therefore, it's very important. Today, if your growth rate or the deposition rate is the reaction rate limiting, it means the growth rate just depends on the temperature. So it's very important to maintain the uniform temperature. Okay. So it's very important to maintain the uniform temperature in order to have the uniform deposition rate. We want to have the uniform deposition rate because we want to have the uniform thickness. Okay. So today, if the reaction rate limited, it means right now the temperature is dominant the growth rate, or the temperature is dominant the growth rate. So today, if you can increase the temperature a little bit, the growth rate will be increased a lot. Okay. So right now you need to make sure you can provide a sufficient temperature. The higher temperature will result in a higher growth rate. Okay. And also uniform temperature can make sure we have the uniform deposition rate. It will result in the uniform thickness. Okay. Uniform thickness. Okay. Due to the same deposition rate. Okay. And how about the second mechanism? For the second mechanism, it's the diffusion rate limiting. Right now, right now, if we can assume we already have a very high temperature, right now we already have a high temperature and high pressure. It means we have sufficient energy right now, okay? Right now, for the second scenario, it means at this moment we already have high temperature and high process, high pressure. It means we have sufficient energy. However, we don't have enough reactant. Reactant is we don't have many reactants. So we lack of reactants. Okay. So right now, the diffusivity of reactant is very important. Okay. So the amount of the reactant will determine the growth rate. Okay. So that's the reason we call this mechanism as diffusion rate limited. Diffusion rate of the reactant. Okay. Diffusion rate of the reactant. So we call it diffusion rate limited. Okay. The diffusion rate means the reactant diffusion rate. Reactant diffusion rate is limited. Okay. So we don't have enough reactant. Okay. So today, if we can increase the flow rate of flow. If we can increase the flow rate of the reactant, if we can increase the flow rate of the reactant, if you can increase the flow rate of the reactant, then the growth rate can be increased. Okay, because today I have sufficient energy, but I don't have enough reactant. Okay, so today if the diffusivity 它的扩散的速度这个反应物扩散的速度快一点，这个反应物是不是会有更多的反应物可以落在 silicon wafer 上面？那我是不是就可以增加我反应物的浓度？So today, if we can increase the diffusivity of reactant, it means we can have more reactant on the silicon wafer. So it means today, if we can increase the flow rate of the reactant, then we will have more reactant on the silicon wafer surface. Then growth rate can be improved. Okay. At this moment, temperature is not so important because I already have high temperature, high pressure. We already have sufficient energy. So no matter the temperature is 100 and 150, so no matter the temperature is 250 or 300, the growth rate doesn't make a big difference. Okay. However, if I can increase the flow rate of the reactant, then the growth rate can be enhanced a lot. Okay. Because right now I already have enough energy, but we don't have enough reactant. Okay. So we say at this moment, this mechanism, we call it diffusion rate limited process. Diffusion rate limited process. Some textbooks also write down mass transport control, or the mass transport control. Okay. Or the mass transport just means for the reactant, we don't have a lot of reactant on the top of our silicon substrate. Okay. So do you still remember when we talk about the oxidation or the silicon oxidation, or we talk about DG model, and we also shows you how the figure here, the y-axis is the oxide thickness, x-axis is the oxidation time, 氧化时间. And we mentioned how we have two stage, right? Or the first stage is the linear region, right? The first stage is the linear region. Or the first stage is the initial growth of the silicon dioxide, right? Or we say it's only 15 nanometer, or only 15 nanometer. Or we mentioned at this moment we have a lot of oxygen, right? we have a lot of oxygen on the silicon wafer surface here, right? Because here is the origin silicon surface. So you see the figure here. And the first moment we have many oxygen, many oxygen on the silicon wafer surface. So right now we have a lot of reactant oxygen, right? We have a lot of reactant of the oxygen. Okay, so just like the first mechanism, today we have a lot of reactant. Okay, so right now the growth rate just determined by the temperature. Temperature is the most important factor to influence the growth rate, because right now I already have a lot of precursor of the oxygen. Okay, so right now just at the first stage we already have so many oxygen. Okay, so right now I just try to increase the temperature. So if I can increase the oxidation temperature from 900 degrees Celsius to 1000 degrees Celsius, the growth rate can be enhanced a lot. Okay, so right now we already have a lot of oxygen. Oxygen is the reactant, right? So at this moment, the temperature plays a very important role. Okay, temperature is important. Okay, so we call the first stage as the reaction rate control. Reaction rate control. Okay, or reaction rate control the growth rate. Okay, reaction rate control the growth rate, and reaction rate just means the temperature. Okay, reaction rate is determined by temperature. So if you can increase the temperature, then the growth rate can be enhanced a lot. Okay, so what does it mean? Reaction rate control. This means just control the growth rate. Okay，所以你可以看到什么叫做反应的速度来决定它的growth rate，决定它的沉积速度。反应的速度是受什么反应？当然是能量。能量越高，反应速度越快。所以 reaction rate 它的反应速度受限在谁？温度。受限在温度，有没有？所以温度越高，它的 growth rate 就越快。那这个前提是什么？前提是我们已经有很多的反应物。我的 oxygen 很多，我的反应物够多，所以这时候反应物不会影响到我的 growth rate， 因为已经太多了。但是我的温度，这时候温度才是最重要的制成条件，有没有？所以这个机制告诉你，未来你在做 thin film 的 deposition， 你要看你的沉积步骤，你的沉积的速度是决定在哪个？是决定在 reactant 的数量，还是在决定在你的 temperature？OK？So like the stage 1, we already have a lot of reactant. So right now, the temperature will control, the temperature will determine the growth rate. So that's the reason we call it reaction rate control. Reaction rate control. Okay. How about the second stage? After we already have like the 15 nanometer of the silicon dioxide. So for the second stage, right now I already have, for example, I already have 15 nanometer of the silicon dioxide. But I still want to grow the thicker silicon dioxide. Then at this moment, the oxygen must pass through, must diffuse, right? The oxygen must diffuse through the silicon dioxide. Then oxygen can react with the silicon here, right? So right now, you see, for the silicon surface is here, right? The silicon surface is here. When the silicon surface is here, you see, do we have a lot of oxygen or not? We don't have a lot of oxygen here, right? Because right now, this is the newly grown, the silicon surface, but we don't have a lot of reactant here, right? So that's the reason today temperature is not important. Temperature is not important anymore. because right now the silicon surface is here, and this silicon surface, we don't have a lot of oxygen. We don't have enough oxygen, okay? So today, if the oxygen can have a higher diffusivity, the oxygen can have a higher diffusion coefficient, the oxygen can diffuse through silicon dioxide more quickly. It means we will have more oxygen and the silicon surface, okay? Then we will have more oxygen on the silicon surface here. Then our growth rate can be enhanced, okay? Also for the second stage, we mentioned for the second stage is the parabolic region. For the parabolic region, right now we are talking about the oxidation of the silicon dioxide. Okay, so we say after we deposit the 50 nanometer silicon dioxide, then this oxygen must diffuse through the silicon dioxide. However, we don't have a lot of oxygen and the silicon surface. So today, if I can increase, the diffusion rate of the oxygen, I can increase the diffusion coefficient of the oxygen. It means if we can let the oxygen diffuse through the silicon dioxide more quickly, we will have more oxygen and the silicon surface. Okay? Then, if we have more reactant on the silicon surface, then the growth rate can be enhanced. Okay? So here, if we can have the, for example, if the diffusion coefficient of the oxygen in the silicon dioxide is higher, then the growth rate can be improved. Okay? So we say it's the diffusion rate control. This process is the diffusion rate control. Diffusion rate of the oxygen. Okay? Diffusion rate of the oxygen. The diffusion rate of the oxygen will control the growth rate. Okay? Diffusion rate of the oxygen. Diffusion rate of the oxygen here can control the growth rate of the silicon dioxide. Okay? It just means the growth rate is limited by the rate. The oxygen diffuses through the silicon dioxide. Okay, so it means if the oxygen can pass through the silicon dioxide more quickly, we will have more oxygen and the silicon surface. Then the growth rate will become higher. Okay, so the second stage will be the diffusion rate control. Diffusion rate control. Okay.那同学可以看到reaction rate control 代表什么？代表说我们有足够多，代表说我们有足够多的 oxygen， 但是我们的温度不够，所以这时候温度只要提高一点，你的 growth rate 就会增加很多。那第二个 diffusion rate control 代表说，这时候呢是什么？这时候是 oxygen 不够多。为什么？因为我已经长出这么厚的 silicon dioxide， 所以 oxygen 在这个 silicon 表面的浓度不够高，所以这时候我们欠缺的是什么 ？reactant oxygen 这个 reactant， 所以这时候我只要把 oxygen 的 reactant 增加，在 silicon surface 的浓度增加，我的 growth rate 就可以增加。这时候你调高温度有没有用？可能影响不大。为什么？因为这时候我主要不是温度影响，主要是什么？主要是我根本反应物不够多，所以你提高再高的温度都没有用。你提高再高的温度，你不管是900度、1000度，我可能10颗氧原子全部都反应完了。但是我这时候如果从10颗氧原子增加到100颗氧原子，就算是900度 C， 我的 growth rate 都还更快。所以你要看的是现在是缺少 reactant 还是现在是缺少温度。所以一个是反应物，一个是少了反应物。少了反应物的话，那当然就是反应物的扩散速度决定你的 growth rate。那如果是少了温度，那就是 reaction rate。reaction rate 它的反应速率会控制什么？会控制我们薄膜的成长速度。OK。 don't worry, you can think about this mechanism later. Okay, later we will talk about this mechanism again. Okay, right now we are going to talk about different kinds of CVD. Because in industry we mentioned mostly over 90% of the thin film deposition is by the CVD. So that's the reason we only talk about CVD. But I also need to show you the PVD, one kind of PVD sputter is also very important in industry. Okay, but we don't go through the sputter, so you can go back and you can Google the mechanism for the sputter. Sputter is one kind of PVD, so you can Google by yourself. Okay, for all of this kind of CVD, I can show you in industry for PECVD and ALD. So those two kinds of CVD are important in the IC fab. Okay, PECVD, HDPECVD, and also ALD is so important. So important in industry. You will use it later. Okay. So let's move on to show you what's the difference between those four kinds of CVD. Okay. So I can classify those two kinds of CVD. The first two CVD are the same. I mean the same means the energy supplier is the same. So today for the first one, APCVD is the atmospheric pressure CVD. It means this CVD we don't have the maybe we don't use the pumping system, so it's not a low pressure, it's the atmospheric pressure. It means inside the chamber inside the chamber of the APCVD, it's just remain 1 atm 1 atm. Okay. However, the other kind of CVD is low pressure CVD low pressure CVD. It means we use the vacuum system to pump down, so the pressure inside the chamber is lower, so we call it low pressure CVD. No matter it's the APCVD 常压的 CVD or low LP CVD, the energy their energy just the thermal energy. We only have the thermal energy in the LPCVD and the APCVD. Okay. However, today if we focus on the PECVD, P means the plasma, E means enhanced, plasma enhanced CVD, or HDPCVD. So when you see those P, HDPCVD means high density plasma CVD, high density plasma CVD. Okay. When you see number 3 and number 4, okay, you will see we do have the plasma. So number 3, we call it PECVD, plasma enhanced CVD. It means we not only have the thermal energy, but also we have the plasma energy, okay? And then for the HDPCVD, this P also means plasma. So for the number 3 and number 4, we have both thermal energy and the plasma to provide the energy, okay? So we have two sources for the energy. One is for the thermal and the other one is for the plasma, okay? And how about the ALD? You see ALD here, right? So we do have the atomic layer deposition. Or maybe later you will have the full name of atomic layer, 原子层沉积. We call it atomic layer deposition, but it's also one kind of CVD. It's course, it involves the chemical reaction. So ALD is one kind of CVD. If we only say ALD, it's the atomic layer deposition, and the energy source is from the temperature, from the thermal energy, from the temperature. Okay. However, today we also has another ALD. We call it PEALD. PEALD. Okay. So PEALD, this PE just like the PECVD, right? PECVD, plasma enhanced PECVD, right? PEALD, just like the PEALD, the plasma enhanced ALD, okay? So for the PALD, and also the other one is ALD. This ALD, some people will call it thermal ALD, but in industry we don't need to say the thermal ALD. Okay, you see, for some lab, they will call it thermal ALD, but in industry we don't need to do that, right? We don't need to show you it's the thermal ALD, because when you see ALD, of course, it's one kind of CVD, so we must use some energy from the temperature to break the bond of the precursor, right? So of course, this ALD is 100% thermal ALD. We have some thermal energy, right? Because we want to break the covalent bond between the precursors, right? So we need to use some thermal energy. So sometimes we don't need to write down the thermal ALD, okay? But don't worry, you just need to know thermal ALD, just the ALD, okay? Usually you don't need to highlight it's the thermal ALD, because usually we will apply the energy, of course, because the precursor has so many elements, right? Because usually the precursor is a compound, so we need to break down all of the bondings. So that's the reason it requires energy, okay? So right now tells me what is the difference between the first CVD and the second CVD with the plasma. For the second kind of the CVD, we have the plasma, like the PECVD, HDP CVD, or PEALD. The energy source, we have the plasma. So one big difference between those two kinds of CVD will be the deposition temperature. Deposition temperature will be different. So for example, you can deposition temperature, 沉积的温度, the deposition temperature will become different. Because for the first kind of CVD, the energy supply only the thermal. So and this we have, it requires 600 to 800 degrees Celsius. Okay, you need a very, very high energy to break bond, to break the covalent bond, to break the covalent bond of the precursor. Okay, so it requires high temperature. However, for the second kind of the CVD, has the plasma energy. So this temperature can be lower. The deposition temperature can be lower. So usually it's 200. So it's just like this range, okay? This temperature range, just for your reference, you can say 250, you can say 200, okay? So this temperature just give you the same. Today, if you have the plasma inside the CVD, usually the deposition temperature is much lower than this kind of CVD, because this kind of CVD, they don't have the plasma energy. So the energy is 100% from the thermal energy. So that's the reason they need to use such high temperature and this temperature just determined by the precursor. So different precursor has the different temperature. So this temperature range, just for your reference, to let you know it's require the much higher temperature than this kind of CVD, okay? So for me, the plasma of number 3, number 4, number 5, you see all of those CVD with the plasma inside the chamber. I think the best advantage will be the lower deposition temperature, okay? It will have the lower deposition temperature, okay? So next time when you see the chamber or when you see the tool has some plasma, the first thing on your mind, will be the deposition temperature is lower, okay? The deposition temperature is lower. So next time when you see the plasma enhanced CVD, or like PCVD, HDP CVD, or PALD, the first thing in your mind, the advantage will be the deposition temperature. Maybe here the deposition temperature is lower, so you will have a lower thermal barrier. This is the best thing for the plasma, the lower deposition temperature, okay? However, I also need to show you, this is good thing, but this is the best. But the best thing will be the, how can I say, the plasma damage. Okay. So today if you have some plasma, inside the chamber, the good thing is the deposition temperature will be smaller, so you will have a smaller thermal barrier. You know, in industry, thermal barrier is quite important in IC fab. So the low deposition temperature is very important to have the small thermal barrier. Small thermal barrier will allow you to have the accurate oxide thickness, and also we can control the junction depth of the source drain. So the small thermal barrier is very important. 为什么在业界我们很重视它的制程温度？制程温度越低，代表它的 thermal barrier 热运算越少。热运算越少，代表我们在长电晶体整个制程过程当中，我们的oxide的厚度才能控制在一个比较小的厚度，oxide的厚度可以控制。然后第二个是 source drain 的 junction 深度才可以控制，不然越高的这些温度都会让你的离子扩散，造成比较深的 source drain 的深度，然后或是你的 gate oxide 都会长得比较厚。OK， so this is the good side of the plasma to have the lower deposition temperature. But also one thing you need to know is the plasma damage. Plasma damage on the silicon wafer. So sometimes we can using some tool design. We can use some design to reduce the plasma damage. Okay. So you need to know for the process we have the good side. But at the same time we also has the bad side. Okay. Okay. Let's take 10 minutes for break.